once again, welcome everyone at our weekly colloquium. Before we start, I have a few announcements. So, as you all know, we have this famous coronavirus in Poland now, and due to this, we have to take some steps, and it is our obligation to slow down the spread of the virus, and because of this, all the seminars starting from now will be cancelled until the 22nd of April. So the first seminar will be 22nd of April. We also cancelled, as you probably know from the email, the meeting of the Scientific Council. So the scientific reporting session, which was supposed to be before this, is also cancelled. We also strongly recommend that all the employees work from home, and in particular, all the employees who are over 60 have to work from home. Please do not come from tomorrow to work for the next 5 weeks, up to 22nd of April. Yeah, that's all. Thank you. And so, okay, good. So now we have the last seminar before the quite long break, and it will be given by Professor Białynicki Birula, and the subject is Berry phase for relativistic electrons. Please.
Thank you very much. So this is the last seminar before the plague. I understand that now we will start counting years before the plague and after the plague. I have had no time to prepare the slides, so I will just use the blackboard, old-fashioned system, and it will be about Berry phase. I think it's a good idea to tell you about the Berry phase because this is becoming a very popular topic in physics. When you write Berry phase in Google, how many hits you get? Make a guess. What?
A lot.
A lot, that means how many? Give an estimate. 75 million. So when it's 75 million, it's worth devoting something to this notion. Well,
By the way, you sent me this beautiful list of the people with the Higgs index.
Ah, beautiful.
But did you check what are those references? I checked at random.
And
The largest number of the largest index belongs to a person who writes papers about the obesity.
yes, yes. Okay, so what is Berry phase? Some of you may have had some ideas, but I will explain it in very simple, plain words. The simplest way to explain it is to use pure mathematics without any reference to physics at the beginning. And then we will start connecting this with physics. Berry phase has a long history, and the mathematical part is much older than the physical part of it. And I was part of this mathematical part, but as my Russian friends would say about the physical discoveries, when they refer to some Russians that were very good, but they discovered it, but they didn't notice. They said, "Обнаружили, но не заметили." And I am sorry to say that that happened also to us when we wrote our book. There is Berry phase in this book on quantum electrodynamics, and it was 10 years before Berry. But Berry came, but not named, unfortunately. But then Berry came, and he has shown that there is very interesting physics in it. But let me start with mathematics, pure mathematics. And it's very simple. Indeed, everybody can understand this. Suppose we are talking about quantum physics. We have a collection of wave functions, which are functions of some parameters. And then, when we have such collection, we can normalize these state vectors to 1. And next step is to calculate the following simple structure. I take the derivative of the wave function, whatever it is, with respect to the parameters here. So I, psi, and then I take the scalar product of this with the same wave function. To make it real, this will be a vector field. If I would like to keep the indices properly distributed, I will write here the parameters as, yes, as contravariant variables. And this field will be real if I multiply this by I. Why it will be real? Because the derivative of the scalar product is 0, because 1 does not depend on the parameters. And therefore, this part is the same as the complex conjugate part. So the field V is real. We have a vector field which depends on a set of parameters. And what can we do with the vector field when it's a function of parameters? We can again differentiate it. And to make life simple, I will now restrict myself to three-dimensional space of parameters. And as Barry wrote in his first paper, this is because we are all familiar with three-dimensional vector calculus. So from now on, the parameters will be 1, 2, 3. And we have a three-dimensional vector now, and we can use it in the following way. Let me first calculate the line integral of this vector field, V. Now I can use the vector notation, which is a function of these parameters, Q. Again, Q are now three-dimensional objects. And I integrate this along some path in Q space.
Actually, it is co-vector field, and this is why you can calculate.
Yes, this is why I changed the indices. It is a covector field. And this object is nothing else but the Barry phase. Barry went one step further because this is even more simple. Namely, Stokes' theorem is telling us that we can convert this into a double integral over the surface that is spanned by this closed. And so we have the curl of V, and we integrate this with the surface element. And this is all. This is everything you must know about the mathematics of Barry phase. And then comes, of course, the interesting question, how is this connected with physics? Well, what we have here is the following problem. We have wave functions which can be manipulated because they depend on parameters. So you can change the wave function by some external action. For example, one application, and this is the first experimental test, and this is what really we missed noticing. Namely, we have photons, and photons have momentum. They can travel in a complicated way, for example, in a fiber. In an optical fiber, you can send photons along such a fiber, and then you can see what is this integral here.
But in this case, it could be classical wave as well.
Of course. Could be classical, sure. But the language, okay. I here will come because what is propagated here is polarization. And the best way to describe polarization is to use the polarization vector. And the polarization vector is a function of photon wave number. So we have a polarization vector here, and again, this is what we wrote in our book. If you differentiate this polarization vector with respect to k, and then multiply it by complex conjugate and multiply it by I, you have a case of Berry phase. And when the photon travels along this fiber, it picks up an additional phase. And in an experiment by Tomita and Chu, they measured the polarization difference between the photon which is sent straight.
Sure, they had strong light. They did not have individual photons.
Of course, but
So this language of photons is kind of...
it's very convenient because photons have helicity, and helicity here plays the dominant role. It doesn't hurt to talk about photons since electromagnetic waves are made of photons. But of course, it was later found that there was an Indian physicist, Paramachandran, who had this idea even before Berry, but somehow he discovered but didn't notice the significance. Okay, so
There is a word, a sentence in the paper by Felix Bloch, when he invented the Bloch function. We make the comment that if the crystal in which we construct the Bloch wave does not have a center of inversion, then if we calculate this integral is different from zero.
yes,
And that's exactly the very phase.
absolutely. This notion is absolutely universal, and I wanted to stress that it's so simple and general that you can apply it in many fields.
Thomas precession, it is also the same thing.
This is the propagation of the of course. And when it comes to propagation of polarization, the first paper really was by an Italian Bortolotti, who in the 20s already found that polarization travels in inhomogeneous medium in such a way that you can write down the non-Euclidean metric that defines the trajectories just using this artificial geometry built from the
Non-uniform medium corresponds, is absolutely equivalent to
yes.
non-Euclidean.
Yes, absolutely, and they have written a metric, etc. Okay. So the interesting physical question is,
One of the most important applications of the Berry phase and all this idea is in Iwo formula with conductance and the quantization of conductance.
yes, yes. There are also some connections with Hubbard model, etc., etc. It's not a coincidence that there are 75 million hits because Berry phase appears everywhere. Now, there is one problem which I will now use as an illustration. This is the electron. And of course, for electrons, there is a lot of investigations, even some of them are here in this neighboring institute. The group of Thomas Dietl is working in spintronics, and in spintronics, Barry phase plays a significant role. But we did it for relativistic systems. So now I change the gears, and now I go to relativistic electrons described by the Dirac equation. So here is the Dirac equation. Hc are equal to 1, and this is the Dirac wave function, and this is equal to 0. The question is, how do I manufacture here the parameters Q, which are needed here to have a family of solutions of the Dirac equation? First, let me make an observation that should have been really made in every textbook on relativistic quantum mechanics. Namely, it's rather tedious job to solve the set of 4 equations. Gammas are 4x4 matrices. So to solve this set of equations, you have to work. But you can have a better method when you do not solve the equations, but you just construct the solution. And the solution can be constructed from any solution of the Klein-Gordon equation. If you have some solution, say chi, of the Klein-Gordon equation, you can immediately construct a lot of solutions of the Dirac equation without any work, except you have to differentiate. But that is easier than to solve partial differential equations. Of course, this is so simple only for non-interacting electrons. There is no external field. I will come to this later. And the method, this works as follows. If you take any constant 4-dimensional bispinor, so it has components psi1, psi2, psi3, just 4 complex numbers. And then you do the following. You differentiate it and form the following. This chi here, I'm sorry, this should be denoted by a different letter. Chi was a solution of the Klein-Gordon equation, so I let it be psi, and this is multiplied by the solution of the Klein-Gordon equation. And if I now this is phi, sorry. This is phi, this is phi, and if I differentiate phi and call it psi, psi will satisfy this equation. Why? Because the product of gamma mu, delta mu plus m times gamma mu, delta mu minus m is exactly the minus Klein-Gordon equation. And this was a solution of the Klein-Gordon equation. So we have a simple method of generating solutions by pure differentiation, provided we have the solution, some solutions of the Klein-Gordon equation. So now let me write a solution of Klein-Gordon equation, is chi, as a Fourier integral, because then one can easily see this is d3p divided for convenience by this normalization factor, useful in Fourier representations. Here I have minus I ept plus I P R, and then any function of P. Why is this the solution of the Klein-Gordon equation? Because this is a collection of plane waves, and every plane wave is a solution of the Klein-Gordon equation, because EP here obviously is defined as the square root of m squared plus p squared. So here we have an explicit formula for the solutions of the Klein-Gordon equation. Now I have to substitute this here, and for simplicity now, and this will be quite sufficient, I will only choose these two components as different from zero. One important remark. Of course, these are not all solutions of the Dirac equation, because the Dirac equation, as Dirac painfully discovered, also has solutions with negative energy. And I'm talking now about electrons. I will not consider solutions with negative energies. That is why the sign here is minus, not plus. So this is a wave function that has positive energy, and this is a good candidate for the differentiation. And now I choose my vector here, this bispinner here, in this simple form, W plus, W minus, 0, 0. What are these coefficients? They will give different spin states. These are two complex numbers that they define different spin states. If I choose the representation of these matrices conveniently, and my favorite choice is what is called the Weyl representation. Some elementary particle physicists call it chiral representation. Then it turns out that these are indeed, as you will see in a moment, coefficients of the spinor wave function. Oh, good. So now we proceed further. We calculate this here, and I have the formula which is useful to show what will come out of this. I'm sorry, I have to write this formula because this will be important for the rest of our study. Now, you know already everything about the Berry phase, so I can erase this and use this green board, assuming that this knowledge is absorbed by the audience. What is then the solution of the Dirac equation written without any pain? It is a family of solutions, and the parameters are W plus and W minus, and this is calculated according to this rule. I take my, and this is what we get. D3P 2 pi to 3 halves, and it's convenient to add the energy in the denominator in this Fourier. Why is that so? Who can say? Professor Kijowski should know. No? Oh, come on. Because this is a relativistic invariant volume element. Yes. So this does not change under Lorentz transformations, and that is why it's convenient to use this. Okay. And now comes the important part, namely this big four-dimensional bi-spinner, and there is MW plus, MW minus, and here we have MEP minus PZ. This will be the longest formula I will use in this lecture, minus PX minus IPY times W minus, and the last coefficient here is PX plus IPY. And it all comes from, as I said, simple plus EP plus PZ W minus. That's all what we need. Notice that I have omitted here the arrow, meaning that I am only considering spherically symmetric wave packets. Why is that so? Because I am interested only in the spin properties of this system, and I don't want the translational degrees of freedom to interfere with my analysis. So we have a family of our functions, and let's proceed towards the construction of the Berry phase. And how to connect this with spin. So far we have two complex coefficients. Now, in what way we will introduce the spin into this game? Well, there is something which is called the spin matrix, constructed from gamma matrices, and it is equal to I divided by 2, gamma mu minus gamma mu. This is the spin matrix for the Dirac particle. It is a relativistic spin, so in addition to our good old friend Pauli spin, it also has the relativistic part. However, this relativistic addition will not play any role. In later, I will only use the sigma ij part. And now what I do is the following. I just want to see what is the meaning of these coefficients here. So I calculate the average value of the spin in this state. It takes some doing. I will not, of course, molest you with this calculation. Of course, to normalize this, I should divide it by psi. Psi, because I have not said anything about normalization. And lo and behold, what happens here is the following. And you will be, I hope, happy to see this. There is W dagger, Pauli sigma W divided by W dagger W. And what is W and W dagger? W is just a Pauli spinner with two components, W plus and W minus. How is that possible? Because, as I promised, the translational degrees of freedom completely dropped out of this calculation because of this symmetry. This is quite complicated. As you see, there are some components of momentum, but when they are integrated over all momenta, they vanish. And that is why this simple assumption that we have a spherically symmetric translational wave function gives this simple result. So we have now, I'm sorry, this is only for the space part, for this part. Of course not, there is no mu and nu. I'm only taking here the space-like indices. That means that Pauli spinner sigma x is equal to sigma 2, 3, etc. Sigma y is sigma 3, 1, and sigma z is sigma 1, 2. So this is the connection of Pauli matrices with this relativistic object. And now we will proceed further. The question is this parametrization that uses two complex numbers convenient? No, it is not, because we moved away from the case that Barry advertised, namely we want to go back to the familiar three-dimensional vector calculus. And what is the way of making this connection? Well, we have to express W in terms of spin. Spin vector is what it is written here. W dagger sigma W divided by W dagger W. This is the spin vector. One can check that it's normalized. This is 1. So we have a spin vector, and spin vector is a convenient control parameter because we know in experiment, that is, some people know how to control the spin. And in this way, we can have control of the family of functions that are written here. This relation can be, this is a good exercise for students because we know that a unit vector such as S can be always written in the form cosine phi sine theta, sine phi sine theta, and cosine theta. This is a standard parametrization of a unit vector in spherical coordinates. We also know that perhaps you have to look in a textbook on quantum mechanics that this Pauli spinor can be always represented in the form cosine theta divided by 2 e to the minus I phi divided by 2 sine theta e to the plus I phi divided by 2. One can check that this is again a unit spinor, and simple exercise in trigonometry. You substitute this into this formula, lo and behold, you get this expression. So we were able to express our W in terms of the angles, but it's not convenient to differentiate with respect to angles. I prefer this three-dimensional picture. So what I did here, before coming here, I just derived the formula for W in terms of the coordinates of the spin vector S. And it takes some doing. Namely, the first component is 1 plus SZ divided by the... In this formula, I disregard the fact that this S vector is normalized because it's more convenient to keep it arbitrary, and then differentiation is much easier. And here we have...
But in fact, you're working on this two-dimensional sphere.
Not really. No. Let me finish the formula and I will comment on that. Here is 1 plus Sx divided by S perpendicular. S perpendicular is square root of Sx squared plus Sy squared. This is S perpendicular. And this is plus or minus I divided by, multiplied by 1 minus Sx divided by S plus. And the lower part of this is the same here except for the minus sign. And the same here except for this plus sign. So this is my W expressed in terms of this. So let me go back now to the, where is my, here. Here is my beloved wave function. It depends on W. When I use these relations, I will have psi, which is a function now of R and T, and Sx, Sy, and Sz. Of three.
Are there any constraints imposed on,
No.
on the W due to
No, I.
just for real two complex numbers?
Yes, there is some peculiarity here, and this is due to the fact that it's not easy to parameterize the sphere without some conventions. Notice that Sx appears here, but Sy does not appear. Still, when you substitute this W here, you get Sy, and that's tricky. If I wanted, because
But this means that there is Sy in S perpendicular.
no, but Sy does not appear. It is hidden in S perpendicular. Sure, sure. But this formula as it is here is only true for... Yes, but it's only true for positive Sy. If I wanted to be, or for it to be true everywhere, I have to put the sign of Sy here also. Okay, so we have a parametrization of psi in terms of three real numbers. And I can now proceed and calculate what Barry would want me to calculate. Namely, I can calculate now this here. It's a lot of differentiation. Of course, I didn't do it. Mathematica did it. It would take me much longer to differentiate this. When you substitute here this for W, you have a mess. But Mathematica, of course, Mathematica needs some polishing because it produces 4 screens of symbols, and then you have to make it simple. And indeed, it can be made simple. So what happens is the following. When you calculate this, you get this vector field, which you need to define the line integral. So I defined the line integral, then I converted the line integral into the surface integral, and what happens is remarkably simple. Let me write the final formula. There is this surface integral, and here, because of this assumption that there are no translational degrees of freedom involved, everything is in terms of...
S does not have any much of the connection with the S.
Sorry, indeed, this is capital S, the surface element. Okay. And this is multiplied, now of course, maybe this is not a convenient notation. This is multiplied by small f, and there is some numerical coefficient that is due to the normalization of this function. I will not bother you. Which, this one? Area. Okay. Capital A plus SZ squared to the power of 3/2. This is the final result of this long calculation, and what is it telling us? Yes, this is the length of the spin, and S. So imagine what is happening here. Yes, but this is how it comes out, because I did not assume normalization during differentiation. So what is the geometrical meaning of this? What is the integral? Remember that dA on the surface is also in the direction of S, is parallel to S. So this is nothing else but the angle, solid angle, subtended by this circuit. So we have a physical interpretation now of Berry phase in this case. Namely, we end up with the following mathematical result, that if you calculate all this, you end up with something which is the same as for photons, which was measured. Now, what is the connection with physics? Now we go back to Berry. In order to realize this in nature, you have to introduce some external element. You have to move your spin along this closed circle, and you can do it by magnetic field. You take magnetic field, you rotate the spin, and what you get at the end is that there is a phase due to this. When you go around, you don't come to the same phase, you pick up an additional phase, the Berry phase, which is an interesting topological property of spinning electrons. Both, because there is some topology here. The curvature here is singular at the origin. Therefore, there is certain element of topology, the same as in the Bohm-Aharonov phase, that you really have this and here also there is this element of, yeah. That's right. Yes.
The fibers are S1,
Mm-hmm.
they need a phase, over S2, this is just the Hopf bundle.
Okay, so this is all I wanted to say. So what you should remember, Berry phase is something very simple when it comes to mathematics. Application of Berry phase to physics is more complicated because it's not enough to calculate these numbers. You also have to show that there is a way of controlling the change of the state of the system by some external means that they will produce the motion, so to speak, of the wave function on a circuit in the space of parameters. Thank you very much.
Okay, do we have any questions? I'm not sure if we should speak to this mic.
What would happen if your starting point was non-relativistic Pauli equation?
I would get absolutely the same result, namely this formula here will be obtained without this hocus pocus. I will directly get to this formula. And what is very pleasant and nice is that relativistically there is absolutely no difference, provided you don't make it too general by introducing some complicated wave packets. This is the non-relativistic Pauli result. Because this is the Pauli spinor in the non-relativistic approximation. Of course, in general, as you see here, this Pauli spinor appears also here in these components, which makes life relativistic. This, you may say that this is the Pauli wave function, two-dimensional.
Okay, I wonder if there is a somewhat simpler derivation of this final result, which would simply rely on the fact that the system is spherically symmetric and you've got the action of the rotational group. I guess you could probably argue that the resulting two-form, which appears here, needs to be rotational invariant, which means that it has to be proportional to the stereographic angle anyway, and then the question becomes of the just the question of the coefficient here, which you could try to calculate at a specific point, which might be a little easier. So my point is that maybe by using the fact that you have the action of the SO3 group here, you can make this derivation somewhat simpler.
Yes, I agree that the final result confirms you, but I always like to work with concrete solutions, and I do not see how to get it without doing some hard work calculating these derivatives. Okay, so here is the starting point. Can you really from this starting point say that this is what will happen at the end? I don't see how, but if you can, then you're welcome. That by just looking at this, I have a collection of solutions of Dirac equation, and they are labeled by some parameters, and then there is some, I'm sure, interesting way of doing it, especially when you connect the spinors with the rotation group, etc.
So basically there's a SO3 group acting in this internal space of this plus and minus.
Yes.
Which induces an appropriate action on the whole space
Yes.
of functions here. And then I guess you could argue that somehow your final two form you get from this, it has to be invariant with respect to this action.
But
you'd have to be careful with this.
notice what happens. As I mentioned, W appears here, 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 and here. When you rotate the spinner, then it's a mess because you get also changes here. And it's only after you do the integration you see that these parts here, which are not relevant, drop out.
Okay, any other comments or questions?
What happens at the singularity point? Because in solid state you can view this part as point of energy gap degeneracy. So is there some analogy in relativistic electrons?
In solid state physics, the situation is a bit different because in real systems you also have spin-orbit coupling, which is essential in spintronics, etc. So I don't see an immediate connection because this is a free motion of an electron, and in solid state, really, however, this question of doubling came up already in the first paper by Berry, who noticed first that the simplest situation is when you have non-degenerate state. And then when you change parameters adiabatically, the system does not leave this state. Then he generalized this to degeneracy, and I think this is what is important in solid state physics.
Okay. I don't see any other comments or questions, so let's thank Professor Białynicki once again.